Welcome to today's paper reading. Today's paper is titled, OpenCodeInterpreter, Integrating Code Generation with Execution and Refinement. This paper was published on the AR14 preprint by Tianyu Zheng and colleagues from the Multimodal Art Projection Research Community and University of Waterloo. The introduction of large language models has significantly advanced code generation. However, open-source models often lack the execution capabilities and iterative refinement of advanced systems like GPT-4 Code Interpreter. To address this, the authors introduce OpenCodeInterpreter, a family of open-source code systems designed for generating, executing, and iteratively refining code. Supported by code feedback, a dataset featuring 68K multi-turn interactions, OpenCodeInterpreter integrates execution and human feedback for dynamic code refinement. The comprehensive evaluation of OpenCodeInterpreter across key benchmarks such as Human Eval, MBPP, and their enhanced versions from Eval Plus reveals its exceptional performance. Notably, OpenCodeInterpreter 33B achieves an accuracy of 83.2, 76.4 on the average, and Plus versions of Human Eval and MBPP, closely rivaling GPT-4's 84.2, 76.2, and further elevates to 91.6, 84.6, with synthesized human feedback from GPT-4. OpenCodeInterpreter brings the gap between open-source code generation models and proprietary systems like GPT-4 Code Interpreter. Code generation has been a significant challenge in computer science for many years. Recently, large language models, LLMs, have revolutionized this field by being pre-trained on extensive code corpora. These models have demonstrated remarkable capabilities in generating code that aligns with user intents, supporting software development. To enhance the capabilities of these models, various instruction tuning methods have been developed. For example, CodeAlpaca uses 20K code instructions generated by applying self-instruct to ChatGPT. CodeEval enriches the complexity of initial code instructions, and Magic Coder generates novel coding challenges. Despite these advancements, current code models have limitations in utilizing feedback for refinement. OpenCodeInterpreter addresses these challenges by integrating both execution and human feedback, achieving superior performance on benchmarks like Human Eval and MBPP, and narrowing the performance gap with proprietary systems like GPT-4. Figure 1 provides an overview of the OpenCodeInterpreter system and its performance in terms of pass-at-1 accuracy on the Human Eval benchmark. The figure highlights that OpenCodeInterpreter 33B, with appropriate feedback, achieves an accuracy of 83.2, 76.4, which is comparable to GPT-4's 84.2, 76.2. Notably, when enhanced with synthesized human feedback from GPT-4, the accuracy of OpenCodeInterpreter 33B significantly increases to 91.6, 84.6, demonstrating the effectiveness of integrating execution and human feedback for dynamic code refinement. The code feedback dataset was created to meet specific criteria for training OpenCodeInterpreter. It includes diverse and challenging real-world queries, structured as multi-turn dialogues, and interleaved text and code responses. The data sources for this dataset are a variety of open-source datasets and coding challenges from LeetCode. To construct the dataset, 3 main methods were employed: single-turn packing, interaction simulation, and code correction. Single-turn packing groups similar single-turn query response pairs into multi-turn formats. Interaction simulation uses GPT 3.5 and GPT-4 to replicate realistic code interpreter usage scenarios. Code correction focuses on boosting the model's error-handling capabilities by generating and correcting incorrect code snippets. Figure 2 provides a summary of the construction process of our proposed dataset, code feedback, and compares it with existing code instruction tuning datasets. The dataset includes 68,000 multi-turn interactions, which incorporate both execution feedback, E.F, and human feedback, H.F. It highlights the integration of these feedback types to enhance the quality of code generation. The figure also contrasts code feedback with other notable datasets such as CodeAlpaca and Magic Coder, showcasing its unique features and improvements in data structure and feedback mechanisms. The experimental setup involves selecting two base models, CodeLlama and DeepSeek Coder, across various scales to demonstrate the dataset's applicability. These models are fine-tuned for 3 epochs with a learning rate of 2 times 10 to the power of -5 and a warm-up ratio of 0.05. To optimize the fine-tuning process, high-quality single-turn data from the WizardCoder 110K dataset is combined with code feedback at a 2:1 ratio, aiming to enhance coding abilities. For evaluation, the framework leverages the HumanEval and MBPP benchmarks, including their extended versions, HumanEval Plus and MBPP Plus, using the Eval Plus framework for a thorough assessment. Table 1 presents the pass-at-1 accuracy of various code models across different scales on the HumanEval Plus and MBPP Plus benchmarks, along with their average Plus scores. The table categorizes models based on CodeLlama, CL, and DeepSeek Coder, DS, and includes baseline results from the Eval Plus leaderboard. It highlights strong baselines and the performance of our methods at each scale. The key metrics include the accuracy of single-turn code generation and the impact of execution feedback and synthetic human feedback on model performance. In the single-turn code generation setting, OpenCodeInterpreter is compared against premier models like GPT 3.5/4 Turbo, CodeLlama Python, and others on HumanEval and MBPP benchmarks. The OpenCodeInterpreter DS33B variant achieves the highest scores among open-source models. For multi-turn code generation, OpenCodeInterpreter excels in iterative refinement, with the 33B model matching GPT-4 Turbo's single-round score. Human feedback significantly improves performance, especially with the 6.7B model. The impact of data sources is also examined, showing that high-quality single-turn data and diverse multi-turn feedback mechanisms enhance the model's capabilities in code generation, debugging, and refinement. Table 2 presents the performance metrics of OpenCodeInterpreter across various data mix ratios of single-turn data and code feedback. The table highlights that the use of execution feedback, E.F, significantly enhances the model's performance. It also demonstrates that an optimal mix of single-turn data with multi-turn feedback mechanisms can substantially boost the model's ability to generate and refine code. The data indicates that integrating high-quality single-turn data can improve the model's multi-turn performance, emphasizing the importance of balanced data sources for effective code generation and refinement. Table 3 presents a performance comparison of the model across various settings with incremental data source integration. The table highlights the impact of execution feedback, E.F, on the model's performance. It evaluates 2 versions of the model, DeepSeek Coder Base 6.7b and DeepSeek Coder Base 33b. The results show how different data source integrations and the use of execution feedback affect the model's performance metrics. In the context of large language models, LLMs, it is now common practice to include code data for pre-training. For instance, PaLM incorporates 5% code data in its pre-training dataset. Similarly, Lambda uses 13% code data, while Galactica includes 7% code data. Other models like Llama, Gopher, and GPT-NeoX have code data ratios of 5%, 3%, and 8%, respectively. Additionally, there are specialized LLMs designed specifically for generating code, such as CodeGen, PanguCoder, and CodeGX. OpenCodeInterpreter represents a major advancement in the field of code generation, effectively bridging the gap between open-source models and proprietary systems like GPT-4 Code Interpreter. By incorporating compiler diagnostics and human feedback into an iterative refinement process, it surpasses traditional one-time generation methods and introduces a new level of adaptability and precision. The ethical considerations in its development ensure a diverse range of coding styles and problem domains, preventing biased outcomes and ensuring data security. However, it is important to note its limitations, such as varying performance across different languages and struggles with extremely complex or ambiguous user intents, which are limited by the model's current understanding and the specificity of the data in code feedback. Thank you for watching.